All right, so now that we have a pretty good understanding of the way P and S waves work, we can now start to look at how we can deduce what the interior of the Earth is made of by observing their actions. So what we have here is a diagram that shows the theoretical travel paths of both P and S waves from a source. So we have a solid inner core of the Earth in the middle, a liquid outer core, and a solid mantle. These are not to scale, of course, but this will do for our theoretical purposes. If we look up at the 0 degree mark at the very top of the diagram, you can see we have a source from which these P and S waves are radiated. Since they travel through solids and liquids, and the solid mantle is solid, then we're able to see the bent paths of the P and S waves as they're collected by seismic stations from 0 degrees to about, looks like 100 degrees down there past the 90. Those, even though the paths are bent, they don't go through any other type of distortion, such as refraction or complete dissolution. Now, after about 100 degrees, we see a shadow zone. A shadow zone is an arc length where we don't see any waves. In this particular case, it's both the P wave and a partial S wave shadow zone. The P wave shadow zone is there because as P waves go through different densities, such as the density difference between the solid mantle and the liquid core, liquid outer core, the waves refract. So we take the fact that we don't see these P waves come out on the other side of the Earth from about 100 to about 145 degrees, and we deduce what that material must be, its density, and also at what angle it must be at. Now we have certain parameters we're able to use, such as we know that the Earth is spherical, so we can say that the layers of the Earth are more or less spherical. So by having that control, we can say what the density difference would be if we expect a certain refraction of the wave as it passes from one material to a different material. Now, we can see that P waves end up showing up again at about 145 degrees, and then we can see them from this side of the Earth down all the way to the southern pole at 180. This model is reflected. If we turn it over, it's just easier to see if we only look at half of it at a time. Now, the S waves we see completely dissolve away from about 100 degrees down until we get to the other side, which would, I guess, be at about 250 degrees. So because of that, we believe that the S waves are not merely refracting, but are completely dissolving. So we think that the outer core is liquid, because it would appear that it's at that depth that we lose S waves altogether. So these shadow zones are what we have used, or what scientists theoretically have used, to determine what the physical properties of the internal layers of the Earth are, and at what depth these boundaries most likely occur.